Cool. Welcome everybody to Control System. This is a TED Talk by Chris from Ryerson Formula Racing, alumni from Controls and Manufacturing System 2019. So basically, what we're going to be going through today is it's like a plethora of what I've gone through on the team, both through the years that I started controls as well as control subsystems such as shifting. So we're going to go through that. Actually, on the front page, and we're going to go through this later, is a cool little H rig for adjusting steering position, fore and aft, kind of like camber and toe, the angles of the grips and such. But we'll go over that more later. Uh, it should be noted that not all information you need to know about controls is in this PowerPoint, because for lack of a better word, it's kind of redundant to put it all in one place. Actually, not redundant, but it's very time consuming. So I'll just get to it. So mainly the first thing you need to know about control system is that a good control system is predictable and allows a driver to attain the fastest and most comfortable performance he or she can in the shortest amount of time possible. A simple yet predictable control system is the entire system goal. Now, F1 drivers have said it before, as well as numerous race car vehicle dynamics engineers. Um, a predictable drive is a good drive, right? A car can only be driven as fast as a driver can drive it. And the point of the control system in its entirety is to make that the easiest or the simplest or the most user intuitive uh, for the user itself. So if you haven't already known, shifter, clutch, pedal box, steering wheel, driver position, and seat are all of what is included in controls as a system. Other teams may differ in team structure when it comes to that, mainly in EV, where there is no shifter or clutch. However, it should be noted that this is what the CV or combustion vehicles use. I'm just going to go over a very quick introduction of what we have done in the past, what their current systems consist of, as well as what's worked for us. Because as far as I know, like I know what has worked on this car from process of trial and error has likely taught us quite a bit when it comes to failure of designed components. So without none other ado, the manual shifter is a simple push-pull cable for actuation. Rod ends mounted on either ends. First rod end is on the lever side or cockpit side. The other side is the engine clevis side. Now, we just use a simple clutch lever mounted to this train conductor style, and it's worked for us in the past. It's also very simple to manufacture and very easy to reproduce and repair. Now, manufacturing as well as design being the main components of this manual shifter, incorporation into the car. It should be noted that these were design goals in previous years and are also design goals moving forward. Um, you might actually see it from this picture, but I'll hit it in the support pictures later that we're going to go through, that they're actually thrust bearings to ensure smooth back and forth operation so that there's no binding between these nylon bushings on the left and right of this shaft collar that's bolted to this side impact tube structure. We've actually gotten rid of this side impact tube structure being round. It had a better I value as well as better stiffness and easier to jig, being a square tube. So we got rid of that at the cost of putting in two tabs in place of this shaft collar. Now, other teams, I have seen other teams do manual shifting with two pull cables. As you can see in the very corner of this picture, there's a little tab. That's called the Bulkhead Tab. It's where two nuts here and here would secure this cable to the chassis, and the inner cable would move freely back and forth within that fixed sheathing. Now, the other teams that I had looked into way back in 2017 and 2018 when we designed this system, and we just beefed it up from when it used to break in RF15. We contemplated other systems like mechanical push-pull systems, as well as double pull cables or double push cables, in which manufacturability and how we could actually make these components played a large factor in implementing them into the chassis. All the components you see in this picture are either bought or made, and bought and made for a very cheap price. Like these tabs here, mounted to the rod ends, were laser cut by a sponsor. This tube was just a simple chassis tube, 075, in diameter. There's a small little cap that we machined that we glued on. This this clutch lever was a bolt-on fix from Amazon, for a motorcycle, so it really wasn't a high-cost system itself. However, it was very effective in completing the system and doing its function, completing its function. Sorry. All right, next is the pedal box. I'm going to just touch upon this because I have a capstone that is from 2018 that is our pedal box that we've grandfathered from 2019 through to 2020. And it's actually a really cool capstone. I encourage you all to read it. I've linked it in the same folder in the member development. I'll show you that later. The actual PDF file is in there. So I highly encourage you go through it on your own time and read through it on your own time, because the process of design is impeccable. It's something not out of just common sense. It's something that they've put thought into quite literally everywhere. So mainly the 3 points I wanted to nailed through about the pedal box. It's arguably the most crucial part of this entire control system, because it is the most designed. And when I say most designed, I say the most amount of hours of engineering principles, from mechanical advantage all the way up to pedal feel, up to newtons per G of deceleration that you could see from the braking force. Everything from that to the pedal ratio of the throttle and the cam design, which we'll also be going through. I have a list here of documents that we're going to be going through. I'll be taking a break at halfway point too, as well, for questions and drinks and pee breaks and stuff. So stick with me. The other two things are that it was designed to maximize human effort. So I'll touch upon that now, but I'll reiterate that later. Newtons per 1G of deceleration. It's also something that our braking system was implemented within, or this was implemented within the pedal box design, because of the amount of variables or constraints needed to design a tangible solution. Okay, cool. This is actually a drawing from the capstone itself. This is just a small part drawing that they had to do back in 2018 for cost report. It was also submitted in their capstone report. So as you can see, there's many parts here. Very small parts: Delrin spacers, cams, barrel adjusters, pedal mounts, as well as heel cups. The heel cups on the bottom aren't shown here, but I do have another picture of them later, so stay tuned. As well as a very thin brake pedal and pedal cups, heel pedal faces with side cups. Now the pedal faces with side cups, these are actually 3D printed out of a carbon fiber reinforced polymer, Mark-forged 3D printer. We'll get more onto that later. It's something that one of our sponsors had done for us. So if you see any of that black material, kind of like the stuff on the RF19 steering wheel, it's a carbon fiber reinforced polymer or reinforced nylon. It's very strong stuff, also very expensive to prototype. and our sponsor has recently gone out of business. However, we will be printing stuff through the DFZ, Design Fabrication Zone, in the upcoming years for CFRP parts. And those are CFRP parts are very versatile, whether you're a CV vehicle or an EV vehicle. These parts need to be prototypes. This thin, I'll get onto the accelerator or throttle pedal later, as well as the brake pedal. But the pedal box was designed to encompass a 4.2 pound weight goal restriction, as well as accompany the current or correct pedal throw for the desired newtons per G deceleration, as well as throttle profiles desired. Next, this is a back view of this. Now, this is actually something I can touch upon now that you have a picture of it in front of you. If you look right here on the left pedal, I'm not sure if you can see my cursor, but number 23, number 22, that's a throttle stop. Now, because they put a throttle stop that would bottom out on the back of the bulkhead, or the anti-intrusion plate, as you would see it. So on RF19 and RF20, you'll see that that blue cone is glued to a plate on the front of the car. The blue cone is glued to the front of that anti-intrusion plate. It's just a small 1/16 inch laser cut steel plate that has been welded to the front of our car, or the front of our bulkhead, and this throttle stop presses on the back of it. Now, the very unique part about this design is that now when you hit the bottom or the throw, or if you hit max throttle on your throttle pedal, now max throttle is actually defined by how many shims, or how many inches of travel you have between your pedal face and that anti-intrusion plate in which it hits and bottoms out on. Now, because the force of your foot on the pedal bottoms out on that face, using the back of the anti-intrusion plate as a structural member to absorb the force of your gas foot, your right foot, you don't need to make a very strong throttle pedal itself. So you'll see that these throttle pedals right here, or these throttle pedal plates, were made originally of aluminum, but we got them reprinted out of CFRP and reinforced with continuous fiber. And we're going to get more onto that later. All right, driver position. So everything you need to know about driver position is that visibility versus ease of operation versus packaging. That three-tier approach. And if you are going into controls and ergonomics, this is one of those things that you will have to do prior to anything on the car, or that this team will have to do prior to anything going on the car. The reason I say that is because the driver sketch is actually the first thing on the car that you design every year. We have not done carbon fiber monocoques, but if we did, it would still be the first thing that we do on the car every year, because it is what gives us our chassis draw around. It's what we draw our chassis around to accompany the driver from the H point, or the harness point, which is the bottom of the where the bottom of the chassis meets the roll hoop, all the way up until the pedal box, which is the length of the car from the front roll hoop, from the main roll hoop to the bulkhead, and everything from a ergo standpoint would be the ergo rig itself, determining what positions of steering position, which would be measured in X and Y coordinates from the H point, would be iterated and tested in an ergo rig. Now, it should be noted that when you're testing in the ergo rig, it's happened a couple of years. I won't say which, but we've had smaller drivers set a really good driver position in the driving rig, or the sim rig, as well as slender people that have set good driving positions in the ergo rig. And these are all good for iteration, and they're all good for testing, and have been tested. However, it should be stated that any drivers that are 95th percentile, to put it in a nice way, or higher, should be put into that rig to be tested as well. This has proved to be a very big problem in previous years where the steering wheel felt too close for drivers with longer arms, or steering or cockpit was literally just too tight. Now, this is a picture of RF-18's driving position, where 5th and 95th percentiles were accounted for. Notice that the bottom hip circle, or where the driver's butt is, the orange circle indicating the 5th percentile female, would be higher than the 95th percentile. You can actually see there's a little gap right there in the bottom. Yeah. Okay, so the whole point that I'm trying to nail back in showing you this picture is that they've actually jacked up the hips, or they've put a foam pad underneath the 5th percentile driver to raise them up so that they are driving in a similar fashion to the, or a similar eye line to the 95th percentile male. Just a point to nail through. Now, this is something I hope you guys can see it adequately, and I hope you guys aren't looking through a phone screen, because I can see it through my phone screen. It's not looking too great. This is an iteration from RF-19's chassis, the driver sketch itself. Now, you can see this this big ugly box that we have right here in the middle. That's a cockpit template. We'll get back to that later. But one thing that you should know that is that because we've grandfathered our pedal box year after year since about RF-18 through to RF-20, with small modifications here and there, we've actually grandfathered a small H distance between, and I say that's H distance because it's a harness point distance, from the point of, you might be able to see it, there's a small blue line here indicating like a line for a driver's femur, and then another small blue line here indicating the driver's tibia and fibia angle, as well as another blue line that's hidden here, which is their ankle line, or their ankle angle. The ankle angle would be 90 degrees constrained, correct? So that you're not holding your foot at a 70-degree angle with respect to your tibia and fibia, which would be quite uncomfortable for an endurance race. Let alone just small operations of the car. But one thing that you should nail through is that there's a small distance here, and it's somewhere hidden in here. You can see it. It's 36.5 inches from the tip of the ankle to the H point. Now, whoever is doing ergo next year, most likely Kyle or Josh. You guys should also know that if you're going to reuse the pedal box in any which way or form, which I encourage you to do with small modifications for EV, that distance is very crucial for 5th to 95th percentile males and females. Now, it should be noted that I forgot where I was going. Oh, okay. So it should be noted that 5th percentile females and males found that their legs were nearly straight when operating the pedals. I think even Amar had troubles straightening his leg entirely and pressing the throttle down entirely, to which we supplemented that problem with foam blocks placed on the pedal cup. Pedal face, to give him the full actuation, full range of motion of the throttle pedal. Now, this could actually be quite dangerous because you don't want to be putting a foam block on your brake pedal. And if that crushes, he loses braking force, and that's not good. That's very dangerous, actually. So that should be looked into definitely. But however, in previous years, 36.5 inches from H point to the ankle point or the heel point has been a magic number. And this driver sketch was superimposed over a chassis to which the pedal box was already implemented into. As well, you should see that up here there is a 18.645 inch H distance for the steering wheel. And now this is where one of the crucial controls downfalls has been in previous years. We've gotten by every year by designing the chassis specifically to dimension it correctly. Now you could actually see that. Oh, sorry to reference that number. That's actually an H distance, an X distance from the H point to the center of the steering wheel. Now, in the FCA rules, it dictates that the steering wheel at no point throughout its rotation or travel should be above the front roll hoop. The front roll hoop being right here. So Errol and I, when we did the chassis design for 18 and 19, um, we actually put in a factor of safety. It was just a half-inch factor of safety right there, just so that if they put a ruler across it, that there was, without a doubt, some space between the top of the roll hoop and the steering wheel in its 90-degree rotation. As well, we would dimension the seat angle, and all of these dimensions are mainly obtained from the sim rig or the ergo rig. Um, I think that's enough for this driver sketch. So driver visibility versus lower CG. This has become a problem year after year, and I'd like to weigh in on it because, and Ariel may vex me if I misspeak this, but I think I've gotten the firewall angles correct. In R17, we tried a 70-degree firewall angle. We didn't actually know too much of what made a good ergo setup in RF17 because RF17 was a rerun or a redo of RF15. It was kind of like take the car, make it better, make it run reliably. But it was a first iteration for ergonomics on this team, arguably. Now it was very easy to drive. We had quite a cramped cockpit. I couldn't find any pictures of a driver in that cockpit, but knees were a bit crunched, like laterally. But it was very easy to drive, and the steering wheel is pointed straight at the driver's face. It was kind of like a bus driver, but you didn't really notice it. CG suffered a little because you're a little more upright, but it was still manageable, and it still set a good lap time, mainly because Keenan was driving it. RF18, very poor visibility comparatively, because of the reclined design driving position. Some drivers liked the reclined driving position. Some people liked the upright driving position. Ergonomics, it comes down to a point of finding a small point or a halfway point between drivers that really like the driving, a reclined driving versus upright. So we tried a reclined driving to see how it would affect our CG as well as a more, in quote, natural F1 feel to the car. But it was a bit challenging to drive and see, especially for shorter drivers. CG was significantly lower in the reclined driver position. However, we didn't have very experienced drivers when driving that year. So to push the car to the point where CG became a very important or determining factor was arguably the trouble. Now, RF19, great visibility. We actually reverted from RF18's recline driving position to a more upright driving position of 68 degrees firewall angle so that we'd have better sight line of the cones. Because one of the biggest downfalls of RF18 was shorter drivers or smaller drivers, anything below 95th percentile, could not see much over the front roll hoop, as well as the bulkhead. I'll get more onto this because it became such a problem in RF18 that when designing the chassis in RF19, we took into account that distance. You can see it's in the bottom corner here, bottom left corner. That's the bulkhead dead zone. So that was, if you draw a line from a 2/3 circle diameter of the helmet down through to the tip of the bulkhead, that would be the sight line. Now, this would be the most obstructed part of the driver, but you could. What I'm trying to say is it would be the most obstructed point directly ahead of the car, as if you had a cone right 6 feet dead center in front of the car, which is not the case 90% of the time because you're looking to the left and to the right of the nose cone, but still should be accounted for. And I think that's it for RF19's driver visibility versus CG. One thing that we did find was, and you've probably heard it, but I'm going to reiterate it, RF19 was tested vigorously on short cones, maybe 6-inch cones. It's kind of like soccer mom cones that you take to practice. Those ones, right? And those are about anywhere from 2 to 6 inches off the ground, and very easy to see if you're driving RF19. And it wasn't until competition that we noticed we kind of messed up in giving such an upright driving position. It gave the driver great visibility and paid off for competitions that use shorter cones. But in Michigan and in FSA North, the cone standard was 18-inch tall cones. So we could see the entire cone from bottom to top, which is it's not something to complain on, and it's not a problem. It's just, that's one of the things that should be noted was we designed this car to be tested with 2 to 6 inch cones, and we get to competition, there's 18-inch cones on the track. They're really easy to see. More visibility is never a bad thing. However, CG could have probably been arguably better. Cockpit templates, I told you we get back to this. Now, this goes upon our rules template. This blue highlighted one right here is the main cockpit template, literally called main cockpit template, that goes from the top of the top of side structure of the car down past the side impact tube structure of the car. And if it hits anything, you do not pass tech. They simply say your template does not fit, there's interferences, we cannot, it's just not rule compliant. And this is a rule in FC competition. Actually, I'll show it to you right here. This is the technical inspection sheet. Sorry, this is the technical aspect of the cockpit opening template, as well as the pedal template, which is the internal cross-section template. Now, this goes from let's see if I can get it back. This goes from right below the steering column to 100 millimeters right before the pedal faces. So 100 millimeters prior to the pedal faces. And again, if these cockpit templates go into the cockpit or go through the cockpit at any point and hit something other than the steering column or steering quick connect, it does not pass competition or rules, tech inspection. It will not. So that being said, this is one of the biggest things other than the driver position sketch that dictates the shape and form of the chassis, as well as the shape and form of the cockpit opening, because that every year is a very tight squeeze for this template. I'm going to go over the support pictures now. Some of these are cool pictures that I found. Not that one. Some of these are cool pictures I've found. I just dragged them off my gallery, and some of them are actually things that we've taken pictures of that I wanted to talk about. So we're going to go straight to this. That's actually a few sim wheels that we've gone through. Really cool stuff that I found online just for ergo purposes. That was another. Let's see if I can zoom into that. That was a cool little shifter paddle design that was single shear from Modena, Italy, as well as a Lifeline. Lifeline is a brand of quick connects with an internal LEMO connector, meaning you don't have any wire coming out of the wheel for electronics on the steering wheel. It's all through the quick connect, which we're going to get into when we go through the steering wheel design because we made our budget quick connect with our budget LEMO connector. It was actually a LEMO connector, but we just didn't pay $400 for the quick connect. Um, uh, yeah, it's kind of funny actually. Now this is something I wanted to get into. Now this steering wheel design, it's great. However, not everyone that trains on this car or drives a car would know or have to use all these buttons. It's something I want to mention as well as touch upon is that there's no padding on these grips. And yes, all of our drivers are supposed to wear uh, gloves of some sort, fire retardant, rule compliant, and everything. But those gloves, yield very little padding, and it's been my finding as well as others that when you 3D print or CNC mill or mold a very hard grip or a hard surface without padding on it, such as this, it creates high points or pressure points on your palms or thumbs or knuckles or hands that would cause pain in that like prolonged use of the product, as well as the actual buttons on the wheel. So lots of these buttons are, yes, necessary. However, may be overcomplicating the design for the fastest attainment or the fastest I know acquiring of the fastest lap time, right? It might complicate the process of operation. Yeah, that's kind of funny actually. Okay, so this is something that we did this previous year. These there's actually three of them. These are just a small, I guess, reminder of modularity. So we didn't know at what point this is our exhaust. We didn't know what would pass exhaust this year in RF20. So we made these small little elbows that could bolt on, bolt off to help direct the test that is sound test at competition to yield a better test or a better test a better sound test result. Sorry. Uh, this is actually something I want to zoom in on. This year and every year, we have to re-weld the steering column. So I wonder if I can get back onto it over here. There's a steering column that passes right through this cockpit template right here. And the cockpit template does maneuver around it as per rules. However, this spline that connects to our steering rack has to be welded every year. So just a note, that's a manufacturing thing that it has to be welded every year. This is a sample product of what printing a paddle shifter looks like. Something I wanted to talk about was the shape of that box meant for a square 10 by 20 millimeter by 2 millimeter neodymium magnet. Now, when you 3D print something, you should also do a test print of some sort, internal or external, to figure out the sizing or tolerance. Just because you print something with a 10 by 20 millimeter box on the inside, kind of like I did here on this paddle shifter that I printed at home, you'll expect 10 by 20 millimeters to come out of that print. But that's not always the case. Sometimes the filament swells and you need to make that box in CAD 10.5 by 20.5 millimeters for it to actually come out as 10 millimeters by 20 millimeters, as well as print bed direction. So, 3D printers, they're coming up in the game. They're very versatile when it comes to manufacturing and prototyping for that matter, and they're not going away anytime soon. So I'm going to say it. This box is offset from the actual plane of the print bed, and that plays a great factor in determining the tolerance in that box that's printed. Now that's printed at an angle. Just a quick note. This is a picture of the seat within RF20. I don't think there's anything more I wanted to say about that. That was the seat finished. That's Kyle standing the seat. That's the seat when it was trimmed. Now, you can see from a couple of pictures ago that there's a nice black grommeting around this seat. That's actually rule compliant. You need to shield or grommet any sharp edges from wires, as well as a safety thing. You don't want to be fraying your wiring harness that your electrical lead has put so much work into. Fraying those like 20 wires or 46 wires that are going through, or the 7 that are coming through the cockpit right on the right side of the driver. You don't want to be fraying those, as well as you don't want to be shifting and using this side of the seat as a knife onto that wiring harness or anything else for like a cable, push-pull cable of any sort. So it should be said that there's also grommeting on the inside for belts. Now, something that they inspect at competition every year is belts. If they're frayed at all or show any signs of wear, cracking, melting, or we actually melted RF18s on the exhaust. I remember that. We couldn't use that harness anymore other than in testing because it was melted. Even though it was a strand of it was an extra part of the harness that was never going to be put under tension if used correctly, they said no. You can't use it. So be very careful about your seat actually chewing away at your belts. It's very common and easily preventable. This is grommeting that has an inlay stainless kind of like structure. You just clip it with wire snips and put it on. It's really not that hard. Cool. That was the before when we trimmed the seat. That was a very nice job by Kyle. That's actually a pretty funny one. Renee put a penny on the ground stud, for luck. And these are the pedal cups that I was speaking about. Okay, so I'm not sure why Google's not letting me zoom into it very much. Hopefully you can see it. These are pedal cups, and we have more pictures of them later, that bolt in the side of each couple of these throttle and brake mount plates. These bolts need to be redesigned because they're extremely hard to service. But it accomplishes the end goal of keeping your drivers heels from bouncing left or right in a high lateral G situation or high lateral G situation with a bump vertically. As well as this white, I think this was, it wasn't nylon, I think it was Delrin. I forget which material that was. Amar will know it because he used it for his wing layups. I believe it was nylon. Anyway, my point was we riveted this nylon sheet onto the gas pedal because late last year early last year we purchased a go-kart, and we thought it was a really cool idea. This go-kart had a roller on this bar gas pedal that it had. It was like a horizontal bar gas pedal with a roller, so that your foot kind of rolled on the gas pedal itself. It didn't have to press on a lever. It kind of rolled on a tube that was like just limply held on. It was a really cool idea, but we wanted to adapt that concept to this throttle pedal by making the throttle pedal constrained left and right so that your foot is constrained by these like little plastic nubs that we 3D printed into the pedal face, but is not constrained in the fore and aft direction where it could slip on this surface. almost quite nicely, so such that it provided like smaller feathering techniques, or it provided ease of feathering techniques for throttle control. This is a side view of the pedal cups. As you can see, this is one of the throttle pedals that we swapped out from that two-plate design. This is a carbon fiber, 39-gram filled throttle pedal, and that's the throttle pedal stop up there that would stop right. You can't see it, but this blue cone is glued onto an anti-intrusion plate. This would hit the back side of that anti-intrusion plate. And that is a bad idea. Next. This is actually one of the things that we've come across with respect to cockpit, but still within controls, arguably, is the shielding of the powertrain from the driver. If you're doing anything driver controls related, you may be tasked with preventing, fuel oversplash from driver cockpit. This was one of the ideas we had to implement to shield that. That's a better look at the flying electrical lead over our pedal box. So the pedal box that I showed you, actually, this one over here, has a dual plate design. Wait, if you could see it, let's see if I can get a better view of this. If you can see it, there is small holes right here. 1, 2, 3, 4, 5, 6, maybe about 10 of them, 8 of them right here, to move the pedal cups or the heel stop fore and aft. Now, because we've never used the pedal cups fore and aft, because the bolt is so GD hard to get, we actually just used the furthest ones and we extended the pedal cups forward. We actually ended up putting this one-sided adhesive neoprene sheet down there, as well as that fell off, but we ended up putting that tack strip. You can find like those little those like slip. You can find them in stairwells on the tip of stairs. They're like little scratchy patches. Scratchy patches, I'm going to call them that. We ended up putting a couple of strips of them there, and actually ankled the driver's ankle. Whatever. That's Jasmine. That's a better look at Jasmine. This is the pedal cups that were unpainted. Very hard to make these. I had to weld the sheet metal. I wish you can see it. You can see it in the corner there. I had to weld the sheet metal and then take a grinder down to it. So they're lightweight, but they're really hard to make. Just a point of view. That was the sheet metal heel cups. Cool. That's a seat mold off of the seat mold, a male-female. I'll get back onto that. This is RF20's dash. You've probably already seen this. That is a headrest that has been wrapped. Also, keep in mind, in competition every year, you need proof that your headrest foam is spec 45.1 every year at competition, as well as, and this headrest does not have it, and we should have it, a hole punch in the side so that they can verify that this foam is the same spec 45.1 foam that you have purchased with purchase order and or shipping label. Cool. This is something that I wanted to look into. Now, you see this U-joint that we have right here. On RF19, it was bolted here as well as bolted here. But some corners were cut, and I wanted to make sure that there was as little amount of play between this shaft here and this shaft here, the upper and lower steering columns, by welding the second side or the pedal side of the U-joint to the lower steering column. And the top one is still bolt on so that we can service this this bushing and thrust bearing assembly. The bushing and thrust bearing assembly is something that is quite unique, and I have Ariel to thank for. Within this system is a spline quick connect welded to a 3/4 inch shaft, which I think you can see it right here. This is 3/4 inch. Drilled to a 1/4 inch sleeved hole, and in that you can see many things are happening here and many things are happening here. This is a washer right here. This first plate here is a washer that has been welded to the tube that is the 3/4 inch tube that this quick connect butts up against. But this washer is actually used as a clamping surface between this shaft collar over here and this washer to fully constrain the this shaft concentrically to this steering column. And the way they do that, or the way we do that, is that we put oilite bushings, which are brass oil impregnated bushings. We clamp them, don't hammer them. We use a clamp to press them onto the chassis, and then we run a 3/4 inch drill through both of them concentrically, so that when we put our 3/4 inch tube through it, it fits and floats nicely through there. But there's still a little play when we do that. So what we do is we put in a thrust bearing assembly on this side of the bushing and a thrust bearing assembly on this side of the bushing. We push it all together, and then we slap a shaft collar, a 3/4 inch shaft collar on the end of that, and that fully constrains this, or fully concentrically constrains this shaft collar assembly to the steering column with very little lateral deflection. There should be there's also some lateral deflection, but that's on the rack side right now, and that's just a worn part. This is a better look at the shaft collar when it's unclamped. So you can see that's your shaft collar, your thrust bearing assembly, and this shaft collar just slips on and is tightened with an Allen key. Really useful. This is the cockpit for RF20. Now, I want you to take note of how the steering column is a single square tube suspended off of the front roll hoop. We've recently switched we've recently switched to a single tube to improve knee clearance when in egress, as well as it was overbuilt to begin with. But we still have these struts right here, these steering column supports, so that this tube does not deflect while steering. Cool. This is a better look at our pedal box. I wish my Google Doc didn't do that. Hopefully you can see it. That is the real life version of the CAD drawing that I showed you earlier. That is the female seat mold that we pulled that male mold off of before. And yes, what we had done was, because in previous years we had used this exact seat mold, and for a different firewall angle, the back and hip angle was different. So what we had done was we had set the firewall angle to the correct angle that we had tested within the rig, you're using the simulator, and we used the rig to align the back angle and the hip angle of this seat to repurpose the mold. And then we just filled it in with a bunch of expanding foam, and then we sanded down the expanding foam, plastered over it, epoxied, etc., 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 mold prep, and pulled it. This is from RF19. This shows you the exact same thing that we used in RF20. It actually looks like the exact same picture, but it isn't. It's a different steering column support. Same washer design with thrust bearings and oilite bushings. It worked really well for us. This was actually when we did. You can see there's a hole right here in right before the U joint. This is actually when we had that LEMO connector fed through the steering column and wires popped out right here. This allowed these electronics not to be wired with an external wire throughout the steering wheel, but through the column itself. which was pneumatic shifting. All right, now this is a picture of Amar in the sim rig. I believe this is for RF20, his driving position. I believe it was. It might be RF19 because it looks fairly upright. Um, Now, this is a great example of what I was saying before. Amar is not a very a big man. Oh, yes, thank you, Kyle. This was RF20. Um, Amar is not a very big man. Sideways or bulk. Like he's a very lean man. And so having him fit into this ergo rig, you can see his knees are almost touching the MDF of the ergo rig. And it is a phenomenal driving position for Amar. Now, if you put Jake or Zach, um, Eurokin in this car, they would have problems fitting into it. Now, this is an exact problem of this situation is even if they had a good time sitting in it, they might have a bad time getting out of it. And considering egress has to be less than 5 seconds, that also needs to be a determining factor for the steering wheel to H point distance that you would design. Okay, let's keep going. This was a vertical view of I don't remember that game, but a vertical view of this sim rig, a side view of this sim rig. And we actually did align the pedals to be at the same height and position that the pedal box would be at in RF20 as well. Okay, cool. On to some other things. This is a pneumatic filling rig for plugging in a paintball tank into an H tank or a T tank of hydrogen or compressed air. This side right here, where the nozzle is, connects to an H tank or a T tank, as well as this side right here. It connects to a paintball tank. There's two valves here. You can see there's a little red little thing there, red little thing there. They're little levers. It basically takes a H tank or T tank pressure and equalizes it through this little channel to a paintball tank for a pneumatic shifting rig. We'll get more onto that later. Now, this is a picture I took of Victoria's, or University of Victoria's steering wheel. Now, when they did this design for their paddle shifters, which is really cool, hopefully you can see it, there's a micro switch right there and two little magnets that are naturally connected that are broken once pushed on these paddles. And it's a double shear mechanism. However, the contacts are exposed. And that's something that I wanted to show because you don't want to miss shift or exposed electrical contacts on any part of your powertrain or anything that controls your powertrain within your system. And in my opinion, it should be against rules. However, it is not. It is a very bad practice. However, it is still being practiced today. It might have been coated with an acrylic nail polish or some sort of coating. However, I could not see from this picture, as well as handling it with my hands, that was the case. So very important to note. We'll also get onto this more when we compare RF18 and RF19 steering wheels. Cool. That was Ohio State's steering wheel. Or sorry, car. Now, what I want to show you was this. This is actually one of the stepping stones of the design from RF18 to RF19 steering wheel. Now, when we had RF18 steering wheel, which I will show you later, we found that the steering wheel was good for some drivers, but not good for others, in the fact that some people complained that their thumbs were too far forward in the steering wheel and they were steering with their thumbs and they had fatigue on their hands because the grips were plastic and they were thick and they were hard to grip. So it was kind of like working out with a thick grip on a dumbbell every time you had to drive the car. And we also played around, you can see this H plate on the back, with the height of the steering wheel with respect to the point or the axis of rotation. That didn't yield many fruitful results. We could have probably done without the vertical aspect of this testing of the steering wheel. However, we still did try it, and we proved that it was a very weird driving style to be swinging the wheel left and right, or kind of like in a crescent moon action about the rotating axis, above or below the rotating axis. It was a very unnatural feel. But because we had these four slits in the top plates, we're actually able to rotate or angle these grips inward or outward, kind of like kind of like a negative and positive camber, like a V or an M, right? We tested that, and I'll get more onto what our findings were later when we go through the RF19 design. Now, this is RF19's complete cockpit, which is great. However, we came into problems where our driver's knees were hitting this dash, or some of our driver's knees hit this dash, and we had to put the same grommet that we put on the seat across this dash, which is, it's nice, but it's this iteration right here was the final culmination of efforts from the carbon fiber layup of the dash panels, which is a very simple layup on an angled piece of foam and cut with a Makita tool to a paper template and riveted to the chassis. Very easy to do if you know how to do a carbon fiber layup, or if a composites department can help you. And these electronics that were once in the RF18 wheel were moved up further into the driver's line of sight. This dash module, however, unfortunately did not work, only because it was exposed to water. I think one of the chips, the mainboard chip, died on it. On RF19, however, there was no wire, as I said, from the wheel to a control module. It was all done within a Quick Connect, an in Quick Connect connector. This was a quick capstone pick. Cena didn't like that. This is a picture from a testing day back in RF19 where Ariel was in the car and he had to wear winter gloves to operate the car, and he was actually quite grateful that the winter gloves could fit the steering wheel because of the larger thumb holes. Because in the RF18 steering wheel, your thumb holes, if you were to do this with winter gloves, would become Chinese finger traps. This is a better closer up picture. You can see a thrust bearing assembly. It should be noted that this thrust bearing assembly should be oiled and lubricated with Mobil synthetic grease, or Mobil 1 synthetic grease, prior to assembly, because it's exposed to the elements. Like it's stainless, but it will still rust given time. Yeah. That is a better picture of a work in progress. This was the RF19. Okay, this is the thrust bearing assembly for the shifter. Cool. Should be right here. Okay, so this is the shaft collar in RF19. You can see there's this tiny little Delrin. I think this is Delrin. Yes, this is Delrin. This nylon infused Delrin bushing that goes onto the inside of this shifter tube. And on the left and right of this shifter tube and I can't zoom into it, are thrust bearing assemblies. Now, this is very useful for shifter binding, so that when I clamp this with a bolt, these tabs, you'd think that these tabs, oh my gosh, they're like 1/8 inch steel, they wouldn't deflect, but however, they actually do deflect minutely, and they do put pressure on these thrust bearings, such that when we had bushings, when these were not thrust bearings, when we had bushings there, we would actually find that the shifter would jam if we tightened this bolt too much. Now that we tighten this bolt, we can lube these two thrust bearings, and they will roll effortlessly, almost as if there's no clamp force there. However, they take the clamp force as a roller bearing force because they are thrust bearings. Okay, this is something I wanted to show everyone as well. This goes upon U Victoria's wheel of exposing shift or micro switch contacts for shifters. Now, what we had done between RF18 and RF19 was take RF18's exposed shift contacts and put them within the wheel, Now, yes, you have to glue micro switches onto a 3D printed paddle assembly, as you see here. However, these shift switches are now protected a lot more than they are from rain than they are in other designs, such as U Victorias and RF-18s. We didn't find any like missed shifts because it was doused with water. However, it's not good for the longevity of the component, as well as the longevity of any electrical component to be exposed to such elements. That's a pretty picture of the wheel. This is the shifter paddles mounted to the back of the steering wheel. This is where the neodymium 20 by 10 millimeter by 2 millimeter magnets sat on the inside here, as well as that 3 printed paddle that I showed you a picture of, and I rambled on about tolerancing before. The other paddle, the other magnet sits, you can't see it, it's hidden here, and because they're such strong magnets, they can act actually through the plastic, which is quite nice. Now, the reason for making these paddle shifters magnetic is not because, oh, they're pretty and they have a nice feel to them and I want to be an F1 engineer. No, it's because they actually give a tactile feedback to a completed shift. If you've ever raced on a sim rig or a sim wheel in which has quiet shifters, or does not have clicky shifters, and you race with headphones on, you'll actually notice that you end up having to shift harder just so you can feel the paddle bottom out, because you lose the sense of hearing the shift when an engine is screaming at 11,000 RPM behind you. So that being the determining factor, I want to give this steering wheel a tactile feedback, and quite a powerful tactile feedback. And as you can see, you can actually add more magnets onto this to adjust the tactile feedback that you get from these paddle shifters, right? You can actually add more magnets onto the back of the paddles as well to make it clickier, so that you know when you've completed a paddle shift. This has given really good results in the past. As well as stainless hardware. These are 440 screws. I'll get back to this later when we go through the CAD design of this, just shortly. But you want these things to look nice for design judges. So you made these stainless hardware into aluminum bushings that were, aluminum threaded inserts that were glued into this carbon plate. I'll get back to that. It's the pretty wheel. That was the aluminum inserts right here that those paddle shifters screw into, as well as little slots for the micro switches to pop through into the wheel, so they can be soldered in the wheel and not externally. This is just processing. This is a aluminum mock-up of the carbon dash panels. This was actually the first iteration. The carbon dash panels was an afterthought and said, hey, look, I can make this lighter by making them carbon, and all I have to do is lay up an angle like that and trim it to one size, right, using none other than a one-to-one drawing. And this is actually the very first iteration of seeing how these dash panels would fit in real life, and if they need to be shortened for driver egress and knee clearance. This was what happens when you, bubbly clear coat. Okay, so this is a story. When we were seeing this in house, the CNC broke right there. You can see where it plunged, and it broke. The CNC servo controller motor actually fried, and I actually had to do the rest of this by hand. So because I had a one-to-one drawing ready, I just glued it over and dremeled the rest out. I believe that this wasn't, no, this was where it broke. But we got this actually water jetted by another sponsor, so we sent that out and we had this done for us too. This was University of Akron. This was taken back in 2019's shootout. Really cool wheel. However, this steering wheel actually takes probably about the same amount of effort that our steering wheel takes, but is I'd say it's about the same. It's the same price to make, only because it's actually a little trickier to make because they have integrated electronics within that layup. So the the wheel, if one of these wires breaks within the wheel, they need to feed drill a new hole within this wheel, within the core of the wheel to feed it through. So the manufacturability of this wheel is kind of like one off. These tack switches that they've glued on don't have back switches, so they're actually physically glued onto the wheel, which is good. You know, it works, it's reliable. But if these tack switches break, you need to swap them out easily. We'll get more into that back on the RF19 CAD. I'm running low on time. I got a lot to go through, so I'm gonna just zoom through these. This is RF18's cockpit. We had two supports from the corners of the front roll hoop down to the main shaft support for the steering wheel. That was our dash. We had all of our dash electronics, which are RF19 dash electronics, in RF18 steering wheel. Yeah, that was not good. This is really cool because this was a 3D printed tube jig for determining steering wheel angle or steering column angle. This was done by a new member at the time. This is the setup of RF18's first iteration and first testing day of the pneumatic setup, or pneumatic testing rig. This was, or pneumatic shifting. This was a paintball tank mounted to a regulator, and down here you can just see a sliver of it is a small little stainless tube that pushes and pulls this shifter clevis right here. You can see there's a little tube here that is from the manual shifter and a big tube here that is from a pneumatic shifter. So when you clicked the paddle, it actually moved the manual shifter as well. This is because you wanted a redundancy in case your pneumatic rig ever failed. Cool. This is that picture of the bolted together H rig, or diameter wheel test, or wheel diameter test, sorry. This is when we had Keenan come in and mold steering wheel grips, and we tried to 3D scan these, and we quickly found out that before we 3D scanned all these grips that our Formula Ford driver, or ex-Formula Ford driver had molded, were fantastic for Keenan, and Keenan loved them. He was so excited to see these go into production. Except the second Ariel or Amar or Daniel or Christian picked these up, they picked them up saying, "Oh, like there's a really high point here. Oh, like my hand doesn't fit this quite nicely." So I actually found out that this wheel on the bottom right here, the Momo wheel as we call it, gave really good results on all the drivers. Even Keenan liked it. Because it had no high points, or no hard points or pressure points to it, because this wheel, above all the others, had padding on it. And so padding, simply put, takes all those hard points out of the wheel, or those pressure points off your hand. So what I did in RF19's wheel was actually, and I'll get back to this. This is Keenan molding the grips and putting it onto the wheel, right? We made multiples of these when CNC'd on this CNC. When we had made that, when we had designed this grip itself in CAD, we actually made this grip thickness right here 1/8 inch thinner on each side of the grip, so that when we wrapped it in like a tennis racket grip wrap of some sort, that it was the final thickness of this Momo wheel, which had such good reviews. And because this Momo wheel had such good reviews and had such freedom in these thumb holes for all your hands, we actually took that into account. And if you can see this, I overlaid RF19's wheel and RF18's wheel in one assembly, so that you could see the difference in the thumb holes as well as the difference in the 3-finger holes. I curved it up on the edge right here so that you could fit your index finger and your your ring finger through these holes and make a full grip on this steering wheel. Let's see. I'm going to zoom through these. UBC. Okay, so these guys, what they did is because they had a steering wheel covering their dash module, which was a Motec dash module, what they did to get past the rule of no steering wheel can be concave or convex of any sort. So if you've ever seen H-type steering wheel, um, Red Bull F1 steering wheel. If you look at a Rebel F1 steering wheel, you see we're not allowed to do stuff like this, where our steering wheel has a concave version or concave top or bottom. They're called H-type steering wheels. We're not allowed to do that because they're considered to be unsafe in Formula SAE. However, UBC got past that by putting a small acrylic piece that was bolted to their wheel here, and you can't see it on the side here, so that they can see through it and see their data acquisition model. I took a picture of that because I thought it was pretty ingenious. That was a testing rig. That's more of our pedal box. That was our pneumatic rig. Very close to the chain. Wouldn't do that again. Put too many bends in these blue tubes where there should have been fittings. Every fitting leaked, by the way. So the more fittings you have, it's kind of like the more bars you have in a 4-bar linkage, the more compliance it'll have. This was the first iteration of the pneumatic testing rig. That was the RF18 steering wheel made. That was a hole that we had to drill. Okay, this is something from a P1 GTR from McLaren. They actually have the H design. Not too bad. But you can notice that if you put your hand over the screen over this box right here, I'll keep on highlighting that, you can notice that this thumb hole and this 3-finger hole is almost directly over each other. Maybe 1 or 2 degree offset, so it looks like a negative camber, you know? Sorry, positive. No, yeah, positive camber, maybe. Okay, I'll get to this because what I wanted to go upon was the design of the steering wheel. When we did this wheel, I'm going to change this, hide this component. When we did this wheel, we designed the structural plate first. So I'm actually going to open this part and I'm actually going to show you the sketch. So right here, we have a bunch of holes. It looks like a complex design. These 3 holes right here are for the quick connect. This hole right here was put in line for the little switch that was going to pass through it, little connector for the electronics. These little paddles, or sorry, these little cutouts are for the paddle switches. These holes are for these outer 6 holes are for the front grip to be bolted through the wheel to the rear grip, which is, I thought, pretty cool because you could embed nuts in the print. Awesome. But something I wanted to show you was this was the actual shape of the steering wheel itself. I didn't draw out the wheel in a 3-dimensional thing. I did a 2-dimensional sketch first. So the actual outer dimensions of the wheel were such that it could fit on the bed of a Markforged 3D printer. That was the literal constraint of this this printer, or of this steering wheel. So 5.20 and 9.65 inches fits perfectly onto a Markforged Onyx X 3D printer that prints carbon fiber reinforced polymer. As well as most of these features are mirrored left to right, so if you pay attention to the dimensions here and here, you can see that I used a constant radius on the outside, a bigger thumb hole with respect to RF18s, as well as I actually printed this out in CNC'd a mock plate with Play-Doh on it to see how realistic this could be, or how realistic this design was prior to actually printing it or sending it off to print. Now, once we finished the 2-dimensional design of this plate, right? We designed the front grip and the rear grip. The front grip being this thing. I'm going to open it. So it won't take long. So the front grip is this thing. And I'll show you exactly in 30 seconds how we designed it. Cool. So it all started with this. It's the same exact sketch as the structural plate. And then we made a little button box, little box extrude for the button box, right? Little face. Then we put a bunch of fillets on it, right? And then after we did fillets, we cut out the box for a head, for a lid. Then after cutting out the lid, we added the first of the paddle switches, which Ariel actually came to me one day and he was like, if you're going to be doing a steering wheel, I really don't like paddle switches, or paddle shifters. I really like button shifters, because he likes what he had trained on was his Logitech driving force wheel, which had button shifters on it at the time, not paddle shifters. So, and by all means, he was a great driver. So I was like, you know what? This needs to be done. It needs to be done. If these switches need to be added or wired in parallel to the paddle shifters in the back, so be it. It needs to be a design that works for all drivers. So that being said, we put in 2 switches for paddle shifters, as well as another couple switches for a launch button, as well as it was going to be a push to talk, but that was actually just a button that was going to be repurposed for later development purposes. And then we added little VHS screw holes so that we could screw in a cover. And then that was the front grip. Now, if I take a wireframe view of this, I want to show you guys something. In these holes in the back, right, there is actually a little cavity here that we printed a little hex nut into, or sorry, we printed a void for a hex nut. And Mikhail, who was our 3D printer sponsor at our time, said that he can pause the print because it prints up from the bed from this back face to this front face, right? He can pause the print at the top of the head, rip out the material, and put in a nut so that he can print over a nut, and he can actually embed a 3D printed nut into the print itself. And I thought that was amazing because he supplied the nuts, and all we had to do was buy the stainless hardware to clamp this side of the grip through the through the structural plate to the back plate using none other than 440 screws, right? And these screws, once you wrapped these grips, were hidden, and they still are, because you wrapped these grips with like a grip tape of some sort. And then after that, you put all these switches in. These actually had little nuts that God forbid if these switches broke, I wanted them to be able to be swapped if they are broken. So inside the wheel, you have all these electrical contacts and shielded by this. You can't. Maybe I can find it. It's right. No, that's the wheel. There's a cover here. Front cover. Shielded by that front cover, which is RF18's or RF19's wheel. RF19's and RF18's paddles were iterated once in RF18, as well as grandfathered the paddle distance from the back of the wheel to the tip of the paddle shifter, as well as the diameter from this center point to this center point, right? I can't select it, right there. And it was denoted in a controls binder. Okay, that is that's steering wheel. What do we have left? Okay, so we have shifting, cam design, and then the final report for JJJZ. JJJZ capstone was actually Jake, Jason, Josh, and Zach, and their capstone. That was their pedal box. Now their pedal box was, I tell you, it was one of a masterpiece, because they I linked this into the support pics as well as the support files. I highly recommend you take a look at it because it's no simple design. Everything that they've done, every fillet, every hole that they've put on that part is well designed. They fully designed their pedal box with, a bounding box of defined constraints as well as operational constraints. Um, Using optimum lap simulations, uh, targeted force vectors. I'm sorry, targeted force in loading scenarios. They wanted to replicate RF 17's performance and improve it because pedal feel was a very iterative process to say the least, and it still is because when these guys designed their pedal box, they actually did a full cam design as well. Now, I'm not sure if I had a picture of this earlier in my support pictures, but there is a small cam. Um, I can actually show it to you in here. In there, right there, if I can show it to you. In here, right here, you can see there's like a little horseshoe shaped thing right there. That's actually the cam thing, so the throttle cam. So when this throttle pedal is pushed, right, it pushes a small cam coupler from this point of view, from this point right here, which is the end lever of the throttle pedal, pushes this cam so that the cam rotates. Now, Josh, that ingenious man that he is, he actually did a really cool cam design doc in Excel, and I've linked this into the support files. He did 3 iterations of linear and non-linear cams that gave different results as well as different throttle resolutions. So we actually have this problem in RF 17 through to RF 20 is that when we press our throttle pedal, it feels like an on-off switch. If everyone can see, this top black line is a linear throttle, meaning for every degree of pedal position, it actually increases by a linear proportion or proportional. Oh God, linearly proportional amount in throttle percentage, as you can see on the left-hand side right here. Now, when they wanted to give a higher resolution to lower throttle positions, meaning they wanted to be able to press the throttle pedal more and get less um, like punchiness to the throttle in lower throttle positions, so that they could easily feather the throttle in mid-corner or when you'd have to throttle the pedal in a load-sensitive scenario. Um, they actually made a non-linear, 3 iterations of non-linear throttle position cams. And it's really cool because the top end of it, if you look at the difference between 80% TPS and 100% TPS, you get the same acceleration, or very, very, very close to the same acceleration that you do at 80% TPS to 100% TPS. So they identified that using dyno curves and uh, uh, logs within our megasquare ECU, and they said, okay, well that part they could just make it wide open so that it just opens the throttle from 80% to 100% almost instantaneously, but gives more resolution to the lower, 0 to 30% of the TPS that's very sensitive, and that would allow our driver to more accurately and more finely operate the vehicle's throttle at lower TPS. Okay, cam radius versus pedal position. Yeah, I'm gonna keep going, not through this dock, but through another dock, so that you guys can keep going, keep with me. Uh, So this is the cam design doc. It's linked in the support files. Support files are in the year two, week two, system theory, and right under our under this design folder is controls and support files. In support files, you'll see there's a bunch of documents here. Uh, Jake, Jack, Jason, and Jake, no, yeah, the capstone that we went through, the pneumatic testing rig that I'm going to go through right now, the shifting presentation I gave back in RF18 to dictate how that system worked, cam design, as well as my controls binder. Cool. I have probably about 15 minutes, and then we're gonna save some time for some questions, and then we're gonna move on. I went through steering wheel. I'm gonna let you guys go through the JJJZ final report in the shifting presentation. Cool. So the shifting basically works. I won't give you the full presentation. Works like this. So you take the potential energy from a carbon fiber high pressurized air tank. Anything above 2000 psi is considered HPA, or high pressurized air, down regulated to 100 to 150 psi, and then fed to two pneumatic solenoids. As you can see here, those pneumatic solenoids look like two little air valves powered by 12-volt signals. Now, 12-volt source with a tactile switch. This side of the diagram right here is actually controlled with an Arduino that was kindly developed and manufactured by our electrical team and lead. So when we did this in RF18, we bolted it to an old engine, and we ran a test rig that was exactly this, a pneumatic cylinder that if you fed air to one side of this pneumatic cylinder, it would push this rod to the right. And if you fed air, giving 12 volts to this solenoid and feeding air to this side of the cylinder, it would pull this cylinder. Now, this cylinder was actually connected via rod end to the engine shift clevis, as shown in the pictures in the RF18 testing. Now, the cool part about this was that you could electrically control these pneumatic valves. All you'd have to do is make sure all your lines didn't leak, all your tank didn't or had the correct pressure, and your regulator was putting out the correct green working pressure to get this right amount of force through this shifter pneumatic cylinder to actually shift the clevis. Easier said than done, because everything leaks and everything has noise electrically, or did. But given our persistence, we actually found out a way to make this work, and it worked phenomenally. And it worked phenomenally for a final drive that yielded a top speed less than 140 kilometers per hour. Now, our top speed for our car right now, I believe, and I'm only speculating because actually, wait, I have a calculation of this. Cool. Our final drive yielded a top speed of, I think it was 150 kilometers per hour, or miles per hour. Yeah. And that was based upon a gear ratio and final drive calculator online that we had used. Now, I think that's about, I don't know what that is in kilometers per hour, but I remember when we did RF18's final drive, we had a lot higher final drive, which was which gave us a lower top speed, which meant more shifting. Now this meant great acceleration. However, we spent half our acceleruns shifting, right? Which was okay, but it made driving the car harder. It made it a lot more difficult. So in terms of powertrain and in controls, interfacing, I guess the only two things that controls and Powertrain really interface on is the throttle input resolution using Throttle Cam tuning, as well as the amount of shifting that is needed, or that is desired in this case. Now, I remember when we did a final drive that was lower, it was phenomenal acceleration when you use this pneumatic testing rig, because it took out all of the complication of shifting, the letting off the throttle so you can push the shifter lever into the next gear, or having to rev match and downshift using the clutch. All of this was automated now because of this shifting setup, and it made driving the car easily 3 times as quick. But it should be noted that it made it 3 times as quick because of the final drive. Like, we had, I think, a full accel run was 4 or 5 shifts for us, whereas a full accel run for us now is, I think, 3, maybe 2. Because we have our final drive set up such that we have a higher top speed at the expense of, we suffer a little in acceleration. However, it's a hell of a lot less shifting. I won't give a TED talk on the shifting and powertrain and drivetrain talk, because I know very little about that when it comes to just the design of the final drive. However, I do know that this severely impacted the operation of RF18 when it had that high final drive, or really low top speed and lots of shifting, versus RF19, where when you bolted this on, it was fun, and it did the trick, and it did shift correctly. However, it was a lot less shifting than RF18. Now, one thing about this system, which is really cool, is that it automates the shifts themselves. All you have to do is know how to click a button. Now, this follows the same controls motto, I guess, making the drive as easy as possible. Because even the easiest of drives are hard to balance a high-speed course, right? Controls job is to make the drive as drivable as possible. So I said it before in layman's terms, but to make the fastest lap attainable at the quickest rate, meaning you could learn the system predictably the easiest. So that being said, that was a whole component design for RF19. Now, we decided to not put pneumatic shifting on RF20 because, frankly, it was such a headache between broken regulators and sourcing parts between RF19 and RF20 that it just became a black hole of time when it came to yieldable results, because we thought, okay, well, we have trained drivers that can drive manual comparatively fast compared to the pneumatic setup, and it would have twice as much serviceability. I could see the system being re-implemented if you had a lot of new drivers, because new drivers, it's easier to pick up a system that's push button than it is rev match and know where to put your hands 3 feet into a corner, right? It's something that definitely takes practice, but having something like this system definitely simplifies that result. I'm gonna leave this PowerPoint up there. It does do a fundamental design process where first off, you put it all in CAD. You figure out your variables, such as your tank calculations. So I want this system to be able to be filled at endurance, or filled right before endurance, and still pass with a regular factor, or an acceptable factor of safety. Meaning, let's say we took this car to competition, we did the first 3 events, and now we've depleted our nitrogen tank, or our high pressurized air tank. I actually designed that filling rig to be filled from a T-tank in the trailer, such that it could be filled to, top line here, 2200 psi or 2150 psi, and it still would have an endurance factor of safety of 2.14 based upon the amount of shifts it would take. And that was done by volumetric calculation of the lines. It's just like PVNRT stuff that you've learned in thermodynamics, minus temperature, because it's not CO2. CO2 is very sensitive to pressure and not nitrogen. And it was really cool because you could find like it was a real life scenario for using PVNRT, which I still to this day have never used PVNRT other than in this one design application, and it was a way of applying stuff that you've learned in lecture to how to estimate how many shifts you'd get out of a specified pressure and volume tank, transferring that volume to a smaller volume, i.e. your lines and your shift cylinders, at a lower working pressure, and how many shifts you would get in charging and discharging, charging and discharging those lines in that cylinder. And expecting your performance for such. And that was actually the theoretical calculation. And we went into the practical. So we actually have two tabs here, 3K tank and 4.5K tank. And this is actually number of shifts and tank pressure that was dictated. And we actually created tank pressure curves based upon how many shifts we would get out of a 3000 psi tank versus how many shifts we would get out of a 4500 psi tank, and how many we would need to do an endurance. So you actually got your how many shifts you'd need to do an endurance, which is 250. And you could actually find how many tank or shifts you would get from tanks of certain pressures or tanks of certain volumes at certain pressures. For example, a T tank normally comes at 2000 psi, right? And we bought a specially ordered 4500 psi high pressurized T tank to recharge our shift tanks that we would just equalize at the end of every day and recharge our paintball tanks to get them above that 3000 psi tank that we could get them filled up at the paintball shop for. And it was really cool because it could show us how many shifts we would get at certain tank pressures, or how many shifts we would get at certain tank volumes. And it wasn't linear. It was not what we had calculated. It was actually significantly less. I think it was like 75% less. And we accounted that for maybe leakage or bad seals within the system. But these things, if they weren't tested, it would have been a downfall of the system. Hence, one of the things that is pointed out in this PowerPoint that I showed you was people who don't have redundancies within that system. So we had in RF 18 and 19 a manual shifter as well as a pneumatic shifter. So the pneumatic shifter was always actuated via paddles on the back of the wheel, but it was also solidly connected to the shifter. So every time you shifted, the shifter within the cockpit would move next to your leg. And we made sure it wasn't going to hit your leg or anything, or hit the driver, or injure the driver of any sort, or come in contact with their hands, because we could adjust the shifter placement to account for such. However, we wanted to keep it solidly linked because we'd seen so many teams in previous years, and it still happens for teams that want to, do the pneumatic shifting route of their CV vehicle. They always pop tubes. They always pop tubes. They always have their pneumatic tubes touching a hot tube of some sort, or a hot engine block, and pressurized air in a plastic tube touching a hot surface, it just bubbles and pops. And if that's your main line, you've just lost shifting. If that's your upshift line, you're going to be stuck in first gear the entire race. And even worse, if that is your downshift line, that you're going to be stuck in fifth gear every year throughout the entire race. And I'm talking about endurance. And that's something that we built this system in parallel to the existing manual shifter system to account for that redundancy, as well as trying to make it the most amount of serviceable, or have the most amount of serviceability as possible. So that tank can be unscrewed from the regulator, the back left of the car, and filled. It can also be filled from a 6-foot high pressurized air line that if you back up the car up into the back white benches of the shop, you can actually hook it up to the T-tank straight to there without unmounting it from the car. Um, Small things like that need to be accounted for, because if you're going to say I want to use this system every testing day, you're going to have to service it every testing day. You're going to have to refill it every testing day. Right? It becomes a consumable of the car. Um, anyway, is there any questions when it comes to that part of the system? Cool. Is there any questions when it comes to the rest of controls? Anything. Anything from dash design to angle of the dash. Um, Actually, that's something that I want to touch upon. The angle of the dash. Let's see if I can find it in support files, support pictures. The angle of the dash, we actually you might be able to see it here. Yes, you can see it here. So when we designed this dash component right here that you've seen in RF19, this is RF19. Oh, sorry. You can see that this dash is roughly perpendicular to the driver's face. That's just a small design decision just to make sure that the display was, illuminating or pointing its LEDs directly at the driver's face. Because sometimes, these those little spherical LEDs that you can solder to a PCB of some sort, they're not too bright unless you're looking directly at them. And sometimes a tack LED is very useful to see while you're driving. So I thought, point it directly at the driver's face so it's the brightest for him. It's not going to blind him. It's just pointed directly at him for usability purposes. All right, I've taken up 2 hours. I think I've debriefed pretty much all of what controls is and what controls does.